some reason the BBC didn't make it. Well, you saw those robots there. They were controlled by microprocessors, by computers. But the robots we have now, some of them are not. They're controlled by a biological brain. And just to explain, on the right-hand side here, we look over there. I'll try not to kill anybody with this laser. We look there, that is the physical robot body that we saw before with the wheels. But on the left-hand side, we've now replaced the microprocessor, the computer, with a biological brain, which is actually grown directly onto an array. This is called multi-electrode array. So the brain of the robot can be a biological brain, completely biological. There's no computer involved in controlling it. There's no human involved. It's just like a brain that you and I would have, with about 100,000 brain cells. So typical human brain has 100 billion, so it's much, much bigger. But this brain so far has 100,000, so it's quite powerful. But essentially the sensors inputting to the brain are the ultrasonic sensors from the robot. The output from the brain are the signals which move the wheels of the robot. What the robot's trying to do, as we will see in a video in a second, is to move forwards and not bump into a wall. A fairly simple task to get it started. This is what we do is we take a rat embryo. So the cells, the brain cells at the moment, are originally taken from a rat. We separate the brain cells using enzymes, so they're all nice and separated. We lay them out. This is our multi-electrode array, so the neurons are laid out in there. Neurons typically are 2 to 20 micrometers. So the typical neuron, the typical brain cell would be maybe 10 micrometers across in diameter. And we see the electrodes. This is how we send signals into the brain and pick up signals from the brain in different electrodes. Some electrodes for putting signals in, some other electrodes for pulling signals out. And they're about 30 micrometers. So it's all at the micro scale. It doesn't have to be at the nano scale. And when we put the neurons down to start with, within about 20 minutes, they start to try and make connections. So these are brain cells, and what brain cells do is communicate with each other, and it only takes them a few minutes, and they're sending out feelers, if you like, in order to make connections with other neurons, with other brain cells. That's within a few minutes. Within 5 to 7 days, we've got quite a complex brain-like activity. So within a week, we've got some sort of basic brain functioning. And what we do is look at where there is good brain-type behaviour and use that to start to drive the robot around. Now, I'll start to drive the robot. You'll see this video. And this is, if you haven't seen it before, this robot, which has ultrasonic sensors, is purely driven by a biological brain. Now, what it's supposed to do is move up towards the wall and then turn to the right. This is what we want it to do. So there it worked perfectly okay, and off it goes, and then when it wasn't supposed to turn. This is what you get with a biological brain. Boom, and it stops. And we have to rescue it. This is the thing with it. This is like a baby brain. It's just been put onto the robot and it's just starting off. So here it is in its early life, when it's like a baby that tries to walk and it falls over. It doesn't get it right, but it gets it bit by bit. It learns, and the neural structures link up together. What we found is that simply the habit of doing this over a few weeks, the connections, the neurons connect up together in a much stronger way, and it becomes much, much better, just from the habit of doing it. But from a research point of view, what we're looking at now is how can we teach it? How can we get it to learn much more quickly? Why are we doing this? Well, in the first instance, we can look at when the physical robot gets into particular positions and see how the brain remembers those positions. How does the memory in this brain actually relate to the physical outside world? Because if we can understand how the memories are functioning, then we can start changing them and helping people with Alzheimer's disease, with stroke patients, all sorts of problems for humans. Now that leads us on to the one final challenge with this at the present time, because this has rat neurons. And of course we can do things with rat neurons fine, maybe it doesn't mean too much as far as human neurons concerned. Well, as it happens, actually dealing with human neurons technically is not too much different. It's quite possible to get human neurons and to then culture them, just as I've been describing, and it will have a more direct relationship as far as the medical results are concerned. If we can see how memories are appearing in the biological brain with human neurons, then that will have a much more direct effect as far as treating Alzheimer's disease patients and so on are concerned. But the problem we have at the present time is not so much a technical one of doing it, but is more an ethical one. How do people feel? I mean, even with rat brain neurons in a robot, some people maybe are not so easy with it, others not a problem. But if we then have human neurons, this is a robot then with a human brain of a kind. A smaller brain than you or I have, but nevertheless it's a purely human brain. How do people feel ethically as far as robots with human brains are concerned? So that's really at the moment we're trying to sound out. Is everybody happy with it? Fine, we'll go ahead and do it, and we'll have, within the next year, robots with human brains. And of course, if we can do that with a little robot like this, then we can do it with much more powerful robots. This is just for something in the laboratory. Let's move on to experiment number 3. This is something that Ray Kurzweil spoke about. Now, I think for this one, because the sound is a bit iffy, I will just talk over it myself. What you're going to see, Ray Kurzweil talked about Parkinson's disease particularly, where a patient has received stimulating electrodes. So this is sending electronic pulses into the person's brain. The main reason for showing this is to see how the brain changes dramatically in its function when it's receiving electronic pulses. So what you're going to see, this is a genuine person who has Parkinson's disease, and you'll see the person with the disease to start with. They've had implants surgically positioned into the central area of the brain, the subthalamic nucleus, right in the centre. The assistants will then switch on the power packs. The power packs are positioned, it's all implanted, but they're positioned here, at the top of the chest, where there's quite a bit of space. There are then wires all underneath the skin, which go into the electrodes deep in their brain. So you'll see how the person is with the disease, and then you'll see how they are with the electrodes switched on. So I'll talk through this. So this is the patient. Typically with Parkinson's disease, what happens is that the person is treated with chemicals, with pharmaceuticals. But then after a while, the treatment wears off, the chemical effects wear off, and the person is left in this condition. This is the person, he can't walk at all. You can see dystonia with the feet joints. He can't straighten his feet joints. He can't really walk without any help. He's confined to a wheelchair. He can't dress himself. He can't get up without help. Can't go to the toilet and so on. So the drugs had worn off, and this is what happens to many, many people with Parkinson's disease. You can see the typical tremors affecting him. Now the assistant is switching on one of the power packs, one of the stimulators, and you'll see the effect of that. It just takes a few seconds to kick in. There we go. And now they'll switch on the power pack on the other side. So this is dealing with the left side of the brain and the right side of the brain. And now the patient is as though he's free again. He's just a regular person, as it were. And he's asked to do some little experiments just to move his hands, but as you'll see, he seems to be